the mean value theorem and Rolle's theorem. The mean value theorem. Assume that f is continuous on the closed interval a to b and differentiable on the open interval from a to b. Then there exists at least one value c in ab such that f prime of c equals f of b minus f of a over b minus a. So what we're going to go ahead and do is break this down. So over here I have an example. Here's f of x, which is continuous on the closed interval and differentiable on the open interval. And what the conclusion says is that there is some place where the derivative at c, so the derivative at c, remember what that means, the slope of the tangent line is equal to f of b minus f of a over b minus a. Well, that's the slope of the line between these 2 points, which we call the slope of the secant line. So notice that's what's happening here. There is some place in between a and b, c, where the slope of the tangent line is exactly the same as the slope of the secant line that connects the 2 endpoints. So here we want to find a point c satisfying the conclusion of the mean value theorem given f of x equals the square root of x on the closed interval from 4 to 9. So let's talk about this function meeting the hypothesis of the mean value theorem. So we need to say that f of x, which is the square root of x, is continuous and differentiable on the interval from 4 to 9. So the closed interval from 4 to 9, which we know is true. As a root function, we can see the graph here. We do satisfy the hypothesis, so for sure there is a point c satisfying the conclusion, and we're going to find it specifically. So we know what has to be true is that there's some place where f prime of c is equal to f of 9 minus f of 4 over 9 minus 4. So f of 9 is 3 and f of 4 is 2. We're just substituting those into f of x. And then over 9 minus 4, that's 5, so we get 1/5. So now we need to find f prime of c. So I'm going to go ahead and do that scratch work over here. So f prime of x is 1/2 x to the negative 1/2, or 1 over 2 rad x. So now this is f prime of x. I'm going to go ahead and put f prime of c, which is just substituting a c in, 1 over 2 radical c here. So 1 over 2 radical c would have to equal 1 over 5. Or really, 2 radical c would have to equal 5 for this to be true. So I'm going to go ahead and drag the work up here. So radical c would have to equal 5 over 2. And if I square both sides, I get 25 over 4. To get rid of the square root, I square both sides. So this is my value of c that satisfies the conclusion of the mean value theorem. Now let's go ahead and take a look at and make sure that it matches what's happening over here on the graph. So we were looking at specifically between 4 and 9, and we want to make sure there's some place where the slope of the secant line, so connecting those 2 points on the function, my f of x, there's some place between 4 and 9 where the slope of the tangent line is exactly the same. So 25 over 4, that's 6.25. So let's go to 6.25 here and go up to the function and draw ourselves a tangent line. And I'm going to try to do my best to make sure it's the same slope. I'm missing a little bit, but it is the exact same slope. So there is some place where the slope of the tangent line is equal to the slope of the. Here we have, if the hypothesis conditions are satisfied, find a point c satisfying the conclusion of the mean value theorem, given f of x equals x squared minus x minus 6 over x minus 1 on the closed interval from -2 to 3. So we have to make sure the hypothesis conditions are satisfied. So we need continuous and differentiable. So if I look at this function here, this function is missing 1 from its domain. So if I substitute in 1, it would make the denominator equal 0. So if my function is not defined at 1, it can't possibly be continuous. So we have a problem. So we'll write something like, note f of 1 is undefined, so f of x is discontinuous between -2 and 3, and we cannot apply the MVT. Now, just to be clear, that doesn't mean that there isn't a point C that satisfies the conclusion. It just means that we can't apply the MVT. We can't guarantee one, but it still might be possible. Let's look at Rolle's theorem now. Assume that f of x is continuous on the closed interval from a to b and differentiable on the open interval from a to b. If f of a equals f of b, then there exists a number c between a and b such that f prime of c equals 0. So an important note is that Rolle's theorem, that's just a special case of the mean value theorem when f of a equals f of b. So if those two endpoints, f of a and f of b, are the same, now the slope of the secant line is 0. So there must be some place c where the slope of the tangent line is the same is also 0. So instead of f of b minus f of a over b minus a, we can simply write 0 because we know the slope of the secant line must be 0. In this example we're asked, does Rolle's theorem apply for f of x equals x to the fourth minus x squared on the closed interval from -2 to 2? And then if so, find all the numbers c that satisfy the conclusion of Rolle's theorem. So we want to make sure and say that f of x is a continuous and differentiable function because it's a polynomial, and then we want to check that f of a equals f of b. So we have our information. We also see that f of -2 is equal to positive 12 after substituting it into the x's. If we plug in positive 2, we get the same answer, 12. So we do know that f of -2 is equal to f of 2. So Rolle's theorem applies. And then if so, find all the numbers c that satisfy the conclusion of Rolle's theorem. So we want to make sure that, or solve for when f prime of c equals 0. Well, the derivative is simply 4x cubed minus 2x, so I'll replace the x's with c's. 4c cubed minus 2c is equal to 0. So I'll factor out a 2c, and I have 2c squared minus 1 equals 0. So I get 2c equals 0 and 2c squared minus 1 equals 0. So c is equal to 0, c squared is equal to 1/2, so c is plus or minus the square root of 1/2. So I end up with 3 different values that satisfy the conclusion of Rolle's theorem, which is fine because it says there's at least one value that satisfies that f prime of c equals 0. So here we have a graph of x to the fourth minus x squared, and I can see that at -2 my y value is 12, at +2 my y value is 12, so my secant line would be horizontal with a slope of 0. And then I can see there are 3 values here where the slope of the tangent line would have to be 0. So if I go ahead and zoom in on that now, I can see there are 3 places where the tangent line would be equal to 0. And these are decimal approximations for our exact value of the square root of 1/2, or radical 2 over 2 and negative radical 2 over 2. In this example, we want to find the point C in the interval between 1 and 3 open, where the slope of the tangent line is equal to the slope of the secant line on the graph of f of x equals x cubed. So here, we know that f of x is a polynomial, so it's differentiable and continuous. So we are looking for where is that value where the slope of the tangent line, that's f prime of c, is equal to the slope of the secant line. That's f of 3 minus f of 1 over 3 minus 1. So we'll go ahead and substitute in 3 and 1. So 3 cubed is 27, and 1 cubed is 1. All over 3 minus 1 is 2. So we have 26 over 2, so we have 13. So now we need to write f prime of c as a function, so we know, well, f prime of x is 3x squared, so we're plugging in 3c squared to solve for c. So this was not the special case of Rolle's theorem because f of a did not equal f of b, but it is the mean value theorem here, so we will solve for c. We will divide both sides by 3, so we get c squared equals 13 over 3. So c is equal to plus or minus the square root of 13 over 3. For this last example, we want to show that the equation x cubed plus 3x plus 1 equals 0 has exactly one real solution. Now we're actually going to need both the intermediate value theorem and Rolle's theorem. So in the intermediate value theorem section, we were able to show that a particular function had at least one real solution, or one real zero. But now we're trying to show that we have exactly one real solution. The other thing that we're missing here is an interval, but we'll get to that. So we're going to start by saying that our function here is a polynomial, so it's differentiable and continuous. So here we have that statement. But now, again, we're missing an interval. And keep in mind, this graph would not be given, nor would the graph be proof in showing the equation has exactly one zero. We would need the full write-up. So what we would need to do is plug in different values and make sure one that comes out is positive and the other that comes out is negative into f of x. Well, we can see that substituting in 0, and that's the first thing I would plug in, gives us a positive value. So plugging in 0 gives us 1. So we'll start there. So we'll say, note, f of 0 is equal to 1, which is greater than 0. And then we would try to plug in another value and make sure that a negative value comes out. Well, the first thing I would try is -1, and we can see from the graph that -1 will yield a negative value. So we'll go ahead and say f of -1, so substituting that in, -1 cubed plus 3 times -1 plus 1 is -3, which is less than 0. So we'd conclude by saying, by the intermediate value theorem, there is at least one place where c such that f of c equals 0. Now we conclude, as we have in the past, we say by the IVT then, there is at least one c in the interval between -1 and 0 such that f of c equals 0. So all we've done is show there's at least one c. So now comes the new part. How are we going to show that there's exactly one real solution? So we're going to learn what's called a proof by contradiction. We're going to start by assuming there are two real solutions and then find a problem with that. So we write, suppose there are two solutions, call them C1 and C2. So that means that f of C1 equals 0 and f of C2 equals 0. So then notice that f of C1 equals f of C2. So by Rolle's theorem, there is a place, there is a c in the interval from -1 to 0 such that f prime of c is equal to 0. There is some place where the derivative is equal to 0. So now that has to be true. If there are two endpoints that are the same and we're continuous and differentiable, Rolle's theorem says there has to be a place where the derivative is equal to 0. So now we are going to search for our contradiction. We want to make sure that f prime of c can never equal 0. So the contradiction is going to lie in the fact that the derivative is always positive. So we want to write something like, however, f prime of x, the derivative 3x squared plus 3, is greater than 0 for all values of x. So the derivative f prime of x, 3x squared plus 3, it doesn't matter what we substitute into x. If I square it, that makes it positive, and then I add 3, it's definitely positive. So that means that f prime of c can never equal 0. So we found our contradiction. So we simply write this is a contradiction, and there must be exactly one solution. So this is definitely a little bit of a lengthy proof, but it is a really great tool to have under our belts to know the different strategies for proof. So we have a direct proof here in the intermediate value theorem showing that there is at least one C. And then again, this was called a proof by contradiction. So we assumed that there were two solutions and then found a problem with that, meaning there had to be exactly one solution.